Hi everybody, very good evening and a warm welcome to Vedantu JEE English. This is your Master Teacher Nabamita Mam and today we are here to discuss periodic property, mind map. Basically, I am going to take care of this session in less than 30 minutes and I'm going to tell you all about the important topics, the important formulas and everything in just about 30 minutes. Why in 30 minutes? Because I think that right now is not the time for you to just sit in front of the screen and waste your time. Right now, it is time for you to actually just revise and self-study. That is why I'm going to finish it in 30 minutes. Let's begin, everybody. Yes, so periodic properties, mind maps and formulas. Here is a little introduction about myself. As you know, as I told you, my name is Nabamita Mam and I'm your chemistry master teacher. Before getting into this whole teaching field, I used to be a research associate in IIT Guwahati and now I'm here. Yeah. Moving on. Let's not waste any time. Now that you are here, do not forget to like, share and subscribe because you know that this is the only English JEE channel. Yes, this is the official JEE English channel of Vedantu. And now moving on from here, let's start with periodic table. Now coming to the question of why a periodic table. Right? Why do we need to classify? Why do we need to group these elements? That's because, hey, we have more than 100 elements. So many elements, if we have to study each one of them one by one, I think it will be very confusing and I think it will be very time consuming. Imagine if you had to study each element and there was a chapter for each element. Can you imagine how tough the JEE exam would be? Even tougher than right now, right? And that is why classification or grouping elements into different categories, it kind of makes it easy, right? It kind of makes it easy. Now what we see, the periodic table that we see today is not how it always looked like. Yes, initially it started with maybe 20-30 elements, but today we have more than 100 elements, right? Out of which some 94 of them are natural and then there are artificially synthesized ones as well. So the periodic table had seen a lot of phases and none of them are something that you can disregard because all of them brought it to where it is. So the first important one that we have to talk about is your Dauberigner's law of triads. Yes. Dauberigner, a scientist who thought that periodic properties are repeating after every third element. So what he did was he grouped the elements in 3 groups, right? Although it was okay to quite an extent, but it could only work till 20 elements or so, but after that it failed. It did not hold good, right? That's when there was another scientist whose name was Newlands. And Newlands thought that just like how a musical notes sound, right? Do, re, mi, fa, la, ti. I think that's the Latin version, whereas in the Indian version you have sa, re, ga, ma, pa, dha, ni, sa. So he thought that the first one and the 8th element, they are similar. And that's why he grouped them in that 8 elements. And he called it to be Newland's law of octaves. Right? Yes? Now what happened? It still did not hold good because to certain extent it was working, but we wanted a law that will hold good for all the elements, right? Yes, and that is when Mendeleev is considered the father of the modern periodic table, right? So what Mendeleev did was commendable. That's what got us to this phase of periodic table that we have now. And Mendeleev thought that yes, periodic properties or properties of elements are periodic function of their atomic weight. Yes, that's what he said. And what he did was there were 6 horizontal rows, yes, like this. This is horizon, 6 horizontal rows which he called as periods, and there were 8 vertical columns which he called as groups. That was Mendeleev's periodic table. But was that the end of it? No. That one person who paved the way to modern periodic table was Henry Bosley, who was working with X-ray spectroscopy, and he actually did quite a lot of experiment and he was working with a lot of elements, and he found out that there was this weird number which he called it Z, was actually related to the frequency of, one second, to the frequency of, I forgot, yes, frequency of the emitted X-rays, right? Frequency of the emitted X-rays. And that Z, that weird number that he called, you know what was that? That was nothing but our atomic number, yes? And from then on, we understood that actually it's not atomic weight, but it is atomic number. It is atomic number that made the periodic table what it is. Now let's come to the bits and pieces of the periodic table and let's try to understand a little bit more about it, right? Now in this chapter, things that are very important is, first of all, ionization energy. What is ionization energy? Oh, well, as we know, ionization energy, like I said, everybody, when you have a cart, let's say that, there is a sale going on in Flipkart, right? Let's say that there is a sale going on in Flipkart and you have got your cart ready, right? You have got your cart ready. Now, if I make a cart here, if this is my cart and there are some items in my cart, tell me something. If I want to buy this cart or if I want to buy the things that are present in my cart, I'll have to spend some money, right? I'll be spending my money will be going out of my pocket, but I will get those things, right? Yeah, so that will make me happy. That will make me happy. And something very similar to this, my dear students, something very similar to this. Let's say that if I have an atom here, if this is my atom and I want to take away one electron, if I want to take away one electron from here, then don't you think that I will have to give this atom something? What will I give? I'll give the atom some energy. I will give the atom some energy to take away that electron. And that is called as ionization energy. This is called as ionization energy. Yes. Now, ionization energy, it's ionization energy 1, ionization energy 2. When you try to take out the second electron, it is ionization energy 2. When you try to take out the third electron, it is ionization energy 3, right? So that you can keep taking out electron. However, it's always, it keeps increasing, right? Yes, it keeps increasing. All right, so that's your ionization energy. Now, how does it, change? When it comes to the whole periodic table, how does it change? Let's talk about it. So, ionization energy in the period, right, across the period, it increases. It increases. Whereas, down the group, it decreases because the size starts to get a little bigger, and that's why it becomes what? It becomes easier for you to take away the electrons, right? Now we come to electron affinity. What is electron affinity? What is electron affinity? Well, we all know that, right? What is electron affinity? We have studied about it. Electron affinity, when you take a look at it in the period, once again you see that in the period electron affinity increases. But down the group, it decreases. All right. Then we come and talk about electronegativity. Actually, tell me something. There is this one property which does not talk about isolated gaseous atom. What is isolated gaseous atom? Taking away one atom, isolated, alone, single, one atom in gaseous state. That's isolated. This property is about shared bond, okay? In this case, we are not talking about isolated gaseous atoms. Electronegativity. Electronegativity is basically when two atoms are bonded together and there is a shared covalent bond. Who is pulling the covalent bond towards them? That atom becomes more electronegativity. Once again, if you remember the example, I had told you chemistry is a shared weight by me and Wasim sir, right? Right? So who is more electronegative, me or Wasim sir? Wasim sir, because he is taking care of physical chemistry as well as organic chemistry, whereas I am only taking care of inorganic chemistry. So he is pulling chemistry a little more, right? He becomes more electronegative. The very same way, you can use the same analogy for what? For electronegativity as well. And we see that in case of electronegativity also, in the period, across the period, it increases, whereas down the group, it decreases. All right, got it everybody? Now, atomic and ionic radii. What is atomic and ionic radii? When we talk about atomic and ionic radii, we understand that atomic and ionic radii is basically from the center of the atom to the last electron. What is the distance? That's your atomic and ionic radii. Now this is the only one that is opposite to all the other properties. Because atomic and ionic radii, you see that across the period it decreases. It decreases. Whereas down the group, it decreases. Atomic and ionic radii, it decreases. However, the group 18, the noble gases, it's huge. Yeah? Alright? Apart from that, there is another property which is called as screening effect or shielding effect. Let's talk about that also. Screening effect or shielding effect. Now what happens is, understand, if I draw this atom here, this is the center, right? This is the center. So understand that there is an electron that is outside. There is an electron that is outside, and if this is the center, don't you think that there are other electrons right here also? In this empty space also there are other electrons who are trying to not let this electron have the full force of the nucleus. Yes, they are acting like a curtain, they are acting like a door for this electron. This electron is not able to understand the full force of the atom, not able to understand the full force of the nucleus. And because these electrons, the inside electrons, are acting like a curtain, we call it as a screening effect or shielding effect. You understanding? So more number of protons or more number of electrons, more will be the shielding effect. However, shielding effect not only depends on that, shielding effect also depends on which block or what block we are talking about. For example, S block, we know that now S block or the S elements, right? The elements that are present in the S block, they have, you know, the orbital shape is round. So if an electron is here, the nucleus will not be able to see it. So they have a very strong screening effect. Now when we talk about P, we try to draw P as this. That means that the electrons which are here and here, they will be easily able to face the full force of nucleus. Correct? Now when we come to D, D kind of looks like this. So you see there are a lot of empty spaces. There are a lot of empty spaces. These are poor shielders. D is a poor shielder, and F is an even worse shielder. Yes, F is an even worse shielder because there are a lot of empty spaces, and the outside electron and the valence electron can come under the radar of the nucleus very easily. So these were the important topics that you had to understand from this chapter. Yes, from this chapter. All right, everybody. Yes. Now, when we spoke about electronegativity, there is certain amount of knowledge that I want to let you know about. Okay, I think my sentence formation has just jumped out of the window. Anyway, electronegativity. Now, in case of electronegativity, we understood that electronegativity is something that you can't really quantify. And that is why various scientists, right, they came up and they said like, I'm going to tell you how to calculate this. I'm going to tell you how to calculate this. Who were these people? Linus Pauling, Alfred Roschow, there was Mulliken, right? They came up with different formulas and they told you about how to calculate it. Let's take a look at those formulas. How about that? Let's take a look at those formulas. Yes, I'm going to show you. So this is how Pauling taught us how to calculate electronegativity. Yes, Pauling taught us how to calculate electronegativity. Pauling said that Pauling said that basically you are putting a root over. Yes, you're putting a root over A and B. Consider A to be one element and B to be one element. Okay, A is one element, B is another element. Now Pauling says that if it is bonded, electronegativity, so it's about bonded, right? It's about two atoms that are bonded together. We're not talking about isolated gaseous atom here. So if these two are bonded, that means how much energy do you need to break it apart? How much energy do you have to give to break it apart? Bond dissociation energy. That's what he's talking about. EAB is bond dissociation energy or bond enthalpy, to break it down. Minus, again root over, you're writing AA, as in if this atom is bonded to another of this same kind of atom, then how much energy do you have to give? Multiplied by B and B here as well. So this is the formula that Pauling came up with, but this is basically the correct formula. This is basically it has to be derived, of course. We are not going to get into that right now. Okay, we are not going to get into that right now because it's just too much. You don't have to know about this. You know this formula, that's enough. That's more than enough. Okay. Now, remember, all bond energies are in kilojoule per mole. Okay. Now, this was not the only scale. There was another scientist whose name was Mulliken. Mulliken also came up with his own idea of measuring electronegativity. And he said that what we can do is ionization energy plus electron affinity divided by 2 will give us electronegativity. Right? And there was another scientist, and there were these two scientists, Hannay and Smith. They said that nothing has a pure covalent bond. There are percentage of ionic character and there are percentage of covalent character. And to calculate that percentage ionic character, what we can do is, it is 16. Delta electronegativity means that what is the difference between the what is the difference in the electronegativity, okay, plus 3.5 and again delta electronegativity. Again, that means what is the difference in the electronegativity between the two atoms, okay. So this is the formula. These are the formulas that you might require if there are numericals, okay. Now coming back to the concept, all right. Let me tell you, ionization energy. Now tell me something, don't you think that there are anomalies? There are exceptions? Of course there are. There always is exceptions, isn't it? When I spoke to you about screening effect or shielding effect, there are anomalies like, let me write it down, anomalies like, beryllium and boron. Yes, where do I write it down? Here. Beryllium and boron, okay, all right, these are anomalies. Apart from that, you also have nitrogen and oxygen, all right. You also have magnesium and aluminium, and you also have phosphorus and sulfur. These are the anomalies, these are the exceptions that you might have to remember, because most of the questions do come from exceptions or anomalies, all right. Apart from that, moving on, when we spoke about electron gain enthalpy, yes, when we spoke about electron gain enthalpy or electron affinity, yes, here also there are anomalies. Do not forget to take a look at those also, all right. Now what are the anomalies? The anomalies are oxygen and fluorine and sulfur and chlorine, okay. It is oxygen and fluorine, sulfur and chlorine. Electron affinity, basically it means that when you try to push an electron, is the atom ready to take that electron? That's about electron affinity. Now oxygen and fluorine, because they are at the top of their groups, you understand that their size is also very small, right? And when you try to push an electron here, they're like, no, we do not need it. We don't need it. So they have less electronic, they are less electron affinity. They have less electron affinity. Understood? Yeah. That's about it. Now moving forward to all the blocks that we have to talk about, let's take a look at it. S block, the group 1, okay, the group 1 in the periodic table, they are known as alkali metals. Group 2 is alkaline earth metals, okay. Outermost configuration is either NS1 or NS2 for group 2, okay. They are reactive and they have very low ionization energy. Of course, take a look at it. The group 1, NS1, they have 1 electron in their valence shell. 1 valence electron. They can easily get rid of it, right? Or they have 2. 2 is also easily, you can just give it away, right? Metallic character and reactivity, it increases down the group. All right, metallic character, it increases down the group. The oxides that are formed by these metals, they are usually basic in nature. We have studied that in our lower grades as well, right? Metallic oxides are usually basic in nature, and non-metallic oxides are usually acidic in nature. Now coming to P block. P block is the extreme right side. Group 13 to group 18. They are also called as the representatives or the main group elements. So is S block actually. Outermost configuration is NS2 NP1 or to NS2 NP6. It can be NS2 NP1, NS2, NP2, NS2, NP3, NS2, NP4, like that till 6, okay? Now at the end of the period, you have those low reactive noble gases. Why? Why do they not want to react? Everybody knows that they have their octet configuration satisfied. Moving on. However, the halogens and chalcogens, they have high negative electron gain enthalpies. Metallic character increases down the group, okay? Metallic character increases down the group. Now let's come to this transition elements, that is D block. They are from group 3 to group 12, okay? Outer configuration is N-1, D1 to 10, NS2, NP6. They form colored ions. They exhibit variable valencies, right? They have lots and lots of valencies, and their paramagnetism. They are also called as the transition elements, and some of them are used as catalyst. Yeah, some of them are used as catalyst. Moving forward to F block, my dear student, they are also called as the inner transition elements. They have the lanthanoids and the actinoids, which we already know. The outer configuration is N-2, F1 to 14, N-1, D1 to 10, NS 0 to 2. All of them are metals. Actinoids, however, are radioactive. If you want to learn about these elements, I have taken the sessions on S block, P block, D block and F block in elaborate manner. However, I would suggest that please put that in 1.25x speed or 1.5x speed and just go through them, so that in half an hour you will be able to finish the academic sessions. All right, just go through them. So finally, here is a chart that summarizes everything for you. You have the electronic configuration here. For S block, it is NS1 to 2. For P block, it is NS2, NP1, 6. For D block, it is N-1, D1 to 10, NS1, 2. For F block, it is N-2, F1 to 14, N-1, D 0 to 1 and NS2. Alright. What is the nature? For S block, it is metals completely. For P block, it is metalloids and non-metals, but some of them are metals as well. D block, metals, all metals. F block, majority of them are radioactive. Alright. Pauling's electronegativity scale I have already explained. Mulligan's electronegativity scale I have already explained, and we had also done with Hannay and Smith electronegativity difference. With this note, this is the end of the session, everybody. Go through this, and I will see you live on Monday at 8:30 with a lot of questions. At least 50 questions. We are going to solve all of it, and we are going to definitely have our JEE rank very soon, right? We're going to kill it there. With this note, everybody, tata, bye-bye. Have a nice day ahead, and I'll see you. Don't forget to study. Bye.